Okay, there we go. Good morning, or almost noon, everyone. My name is Ivan Rangelov from Danfoss. My focus is industrial heat pumps, and I'll present you what can be used like heat pump in process cooling and heating in food and beverage applications. There are many questions when we talk about industrial heat pumps. Let's try to answer the first one. What is available on the market? Up to date, there are commercially available technologies which can get us to heat sinks up to 100 degrees centigrade. These are products which are mature enough and available on the shelf. Okay, but the potential of heat which you can address with these technologies is, let's say, 8% in process heat. So what is next step? Next step is going above 100 centigrade. Why? Because you need to generate steam, often low pressure steam, in among others food and beverage applications. The next step, which is, I believe, very close in terms of development of technologies, is 130 degrees condensing. With 130 degrees, as a first step, you can generate low pressure steam, a 2-bar, which is often sufficient in multiple food and beverage processes. If higher is needed, then you can recompress it with MVR, vapor recompression cycle. So there are also various end-use applications. But again, where would you start? For me, coming from refrigeration, it's most obvious to look in applications where you have combined cooling and heating. You have obvious heat source, right? Firstly, and secondly, you do not require necessarily very high heat sinks. I would say that maybe 99% of food and beverage industry would be covered with low pressure steam generation. And also, as you can see from, sorry for the slide, but from Cordin's study, food and beverage is the largest potential. One of the examples which I found very relevant for being in Bavaria is brewery. Why? Well, I'm not an expert at all, besides end user of beer, but there is a lot of consecutive cooling and heating. So you cool down stuff, then you heat it up, then you cool it down again, then you heat it up. Usually you would use a refrigeration system to cool it and fossil boiler to heat it up. However, you can get rid of the fossil burner, or at least substantially decrease the use of it and combine cooling and heating. But it's a bit more complex than this. But generally, why to waste the heat? Why to reject it to the ambient and not to reuse it, not to lift it to a higher level? Right? We talk about decarbonization of industry. So, which technologies can get us there? Well, let's start simple. We talk about cooling and heating, which means cooling down to negative temperatures, refrigeration, minus 20, minus 30 maybe. Well, not necessarily in brewery, you don't go that low. But if you need to generate steam, you need very high temperature lifts. And the compressors usually would give maximum lift in one stage of 80-90 K, which basically means that with one simple system, one-stage system, you can never cover both cooling and heating and definitely not generate steam. But okay, how can you do that? Then you can combine several of these one-stage systems in cascades. But which refrigerants can play a role? Here we give example where we simulated with our compressors what happens where we simulated multiple refrigerants, a lot of hydrocarbons and some low GWP refrigerants. And we show the envelopes of the compressor from very low temperatures with some hydrocarbons like propane. You can do refrigeration down to minus 25. If even lower is needed, you can have a subcritical CO2, even lower. And in theory, you can have evaporation of hydrocarbons, or rather condensing, up to 200 C. Now, if that is realistic or at all needed, that's another question. But how to combine systems? You make your homework, you map what are your sources which eventually will result in certain evaporating temperature, then what are your sinks which will result in certain condensing temperature. And then you see where you have an overlap between the envelopes of the refrigerants. You need, I would say, 15, 20K overlap so the compressor can operate safely in between. Where we are now? We are now up to 130 degrees condensing. This is what we focus on with high readiness in our components and our compressors. One of our projects is in a brewery in the Netherlands, where earlier this year the task was, together with our partners in Netherlands, to replace a very old refrigeration system for the cooling part, and the target is to replace a gas boiler for the process heating. And we do that with 3 units completely with hydrocarbons. How does it work? The bottom side is reversible chiller heat pump, where we have a propane system, which is chilling glycol for the brewery. Then if heating is also needed, then we send the discharge gas to the cascade heat exchanger. If heating is not needed, then we send it to the condenser, so only our refrigeration circuit works in chiller mode. If vice versa, there is no cooling required, but there is only heating, then we reverse the cycle and then air becomes a source for the second stage. Ideally, both cooling and heating will work 100%. However, life is not such. You don't necessarily need heating when you need cooling, and definitely you need to account for load balancing. Heating. That was a bit fast. So, heating. First stage, generating 90 degrees hot water with isobutane. Source of 40 degrees centigrade, either waste heat from the cooling system, or there is also the water tank with waste heat from processes. So we switch between sources upon availability. And then the third stage is the most interesting one. So up to here, everything, as I said, is off-the-shelf product. Compressors, different technologies, components, it's there. And, well, it works. I was in the breweries. What is the next stage? This is generating 2-bar steam, where we use, again, a hydrocarbon, but it is butane this time, where source is return water from processes at 60 C, and we evaporate at suction 50. For now, we have condensation of the butane at 131 degrees, where we heat up water, pressurized water, up to 128 degrees. After this, we flush it down to 2 bars, and we get steam saturated at 2 bar 122, 24 degrees, if I'm correct. So what is the readiness of this component? Well, we have been working with this application already 2 years also in DTI, the National Technological Institute. We participate in Superheat project, and we have a couple of other projects where we already have some experience what is happening with the equipment at these temperatures. We know that it works in a lab. However, to know what happens over a period of time in the industry, you really need to work closely with the industry. So we have been doing that already a couple of years. I believe that in a couple of years more, so next event, I hope that I'll be talking here and I'll say everything is commercially available. But now we are at readiness level of 8, 9, I would say, over here. This looks nice. It's very flexible system. You can have only cooling or only heating. You can switch on and off stages, make load balancing. But it's good because it is a greenfield project. It's a new project. Most of the projects are not really there. A typical system in a brewery or another food and beverage site existing would be the good old ammonia 2-stage system, fantastic refrigerant for cooling stuff. Well, if you want to generate hot water up to 90, maybe on a good day 95 degrees centigrade, then ammonia is fantastic heat pump to put on top of the existing system. It will have very high COP. However, if you want to generate steam, then with minor exceptions, ammonia is not there yet. What is there and can be done is hydrocarbons. You can connect in a cascade after the high stage of the ammonia. And then just like the previous project, you can lift to 130 degrees condensing, generate steam at 2 bar. Logic is the same, but there are a bit more challenges. Among others is, okay, typically ammonia would condense in a refrigeration at 30-35 C, depending where in the world you are. But we need to elevate the condensing pressure to get to a proper source for the second stage, for the hydrocarbon. So this will have a penalty on the ammonia system, but you need to make it also in a smart way, as you don't need all of the compressors of the ammonia side to lift to the higher pressure, I would say 50 C. You need maybe one. You need to account for load balancing. This is the second challenge. You may have several megawatts waste heat from the ammonia system, but you don't need several megawatts process steam generation for your production, right? So you need to account for balancing of the load. And then, why butane? There are various hydrocarbons. Well, we have tried to investigate a few. Butane is a good one, as it has a reasonable displacement required versus next step would be pentane, which has a higher critical temperature, a bit better COP. However, you need 2.5 times bigger compressor. So bigger compressor, bigger components, bigger money, no business case. These are a few of the considerations. I'll wrap it up. Hydrocarbons are good for new projects, can be also good for existing refrigeration systems. However, it's a bit more challenging to integrate. And we talk a lot about hydrocarbons. They are fantastic refrigerants, but people are getting nervous from them. Why? Because they are classified as explosive. Now, yes, they are classified as explosive. However, we need to treat every refrigerant with respect. And this applies the same for the hydrocarbons. People are not having a problem to smoke cigarettes next to their barbecue, but they get very nervous if there is a closed circuit of hydrocarbon in a refrigeration system. So we need to play it smart. And from technical perspective, with hydrocarbons, you can go to these higher temperatures. Also with low GWP refrigerants, you can also go to these high temperatures of condensation. There are some discussions on political level about the future of low GWP refrigerants. I don't know. We are engineers. We look into what is technically possible and what is the best solution. What is Danfoss looking into in terms of compressors? That's a busy slide, but I'll try to make it simple. We have various technologies. This is why we don't argue for what is one compressor doing better than other. No. There is not one technology which is the best, not in terms of refrigerant, not in terms of compressors. You always need to look into what fits better to your application. And let's look into up to 80 degrees centigrade. For smaller sizes, we see the future with, the now, because we already use them, with scroll compressors, larger scroll compressors, then going to 300-400 kilowatts, maybe 500 kilowatts. You can also go with several scroll compressors, but you can also go with semi-hermetic piston compressors. For larger capacities up to 1.5 megawatt, we also have our collaboration with screw compressors. They are all visible in Cool Selector. Then what is more interesting is up to 100 degrees centigrade. We have the strategy of dual approval for low GWP refrigerants and hydrocarbons in all of our equipment. For again, smaller sizes, up to 400 kilowatts, we have a new development which is on our booth today, which is approved for isobutane, 100 degrees condensing, scroll compressor, and with ZT as well. We can have 3 of those in a manifold. Today, the thread volume is 140 cubes per hour. One compressor, so 3 times 140 can get you to, maybe 400, 500 kilowatts, depending on the conditions. Then we also can go with isobutane in our semi-hermetic pistons and screw compressors. Transcritical CO2, that's not new, and it's also not going above 100 C, but up to 100 C, we also look into CO2, and we have, I would say, complete solutions. Above 400C, how we see the future, or at least the next step, this is butane. This is what is happening now. And ZD, up to 130 degrees centigrade condensing. We have, I would say, few projects for a couple of years now with Bock. We continue getting experience with it. And next year we start also project with our screw compressors with Palladio. We also want to get there. So all of our technologies in compressors, they have aligned development roadmap. Well, that's it for me. Please feel free to reach out, hopefully, over here after the chat or at our booth. Thank you, guys.